Module 1, Lesson 7, Associated Ratios and the Value of a Ratio. Associated means they're connected with each other. And the value of the ratio is where we're actually going to start to find some numbers that we can use to solve problems mathematically, I guess is probably the best way to put it. We'll actually find the value of the ratio and then be able to perform operations with it like multiplication or division. All right, learning targets. Well, we are going to be doing comparisons. We are going to be in particular looking at part to part and part to whole, not looking so much as whole to part ratios in this particular lesson. And we are going to be doing a little bit of reasoning here about changes, but really we are looking back here at making comparison within the wholes, and we're expanding our understanding of what these comparisons mean. We're really taking a deeper look at what happens when we make this comparison. All right, I can statements. So we are going to connect ratios as fractions, which is a big step in using the value of a ratio. We need ratios to represent them as a fraction, so we can use the fraction to solve problems. And in turn, we should be able to take a fraction and we should be able to write it as a ratio. We should be able to find the value of the ratio, which is very much connected to finding this ratio as a fraction. And then we're going to find and write part to whole ratios. We've already worked on this a little bit in class and other lessons, but we're going to be much more direct about what we're doing here. All right, so taking a look at example 1 here, which of the following correctly models that the number of red gumballs is 5/3 the number of white gumballs? So I really need you to pause here. I need you to think this through. Which of these is going to show that the number of red gumballs is 5/3 of the number of white gumballs? So let's take a look at what each of these illustrations is showing us. So we've got the red gumballs and we've got the white gumballs. And it says the red gumballs is supposed to be 5/3 of the white gumballs. So if we take a look at this fraction here, this 5/3, we notice that the denominator is 3. And the denominator of 3 means that it takes 3 parts to be 1 whole. And if the red gumballs are 5/3, that means that it's going to be more than 1 whole. Now the whole in this case is the number of white gumballs. 5/3 of the white gumballs. So if we take a look at this, do we have the white gumballs as being a whole of 3? Well, we see 1, 2, 3, 4, 5 parts there. That doesn't match this denominator of 3 parts here for the white gumballs. On top of that, it says that the number of red gumballs is 5/3 the white gumballs. So I should have more red gumballs than I have white gumballs. So I'm pretty sure that model A here is not showing what I'm looking for. And then I'm going to look down here at model C. I know I'm not going left to right, I'm just going vertically, but let's take a look at C. Well, in looking at A, I've already decided I should have more red than I have white. So that's a good thing on this model. I do have more red gumballs than white gumballs. But once again, noticing that it says I should be having 3 parts for the white. And I only have 2 parts. And the red is 3 parts. So I'm looking at this and thinking the red gumballs are 3/2 the number of white gumballs instead of 5/3. Oh, I should step back up here to A. A, the red is 3/5 of the white. These 3 pieces right here, 3/5, 5 pieces. The red are 3 of them, 3/5 of the white. So let's jump over here to D. And once again, I notice the white gumballs are more than the red gumballs. Kind of the same problem I had up here with A. I should have more red than white. I should have 3 white to make a whole. 1, 2, 3, 4, 5, 6, 7, 8. Well, that doesn't look like 3 parts, does it? And on top of that, the red isn't more. 1, 2, 3, 4, 5. Now, in this case, the red is 5. That's good. But the 5 red is equal to 5/8 of the white. No, that's not really working for me either. So taking a look at B, the white, I've got my 3 parts. I have more red than white, and I have 1, 2, 3, 4, 5. I have 5 thirds. The red is 5 thirds of the white. Here's the 3 thirds, which matches up with 3 thirds, and then I have 2 more to make my 5 thirds. Now, you might be feeling a little overwhelmed. Boy, that went really fast, but I need you to stop and step back here and think for a second, okay, what do we know about fractions? Fractions have denominators. Denominators tell us the total number of pieces to make a whole. So this denominator here says that 1 whole is going to be 3 pieces. And it says the number of red gumballs is 5 thirds the number of white gumballs. So the white gumballs, that is the 3 pieces. And it tells us the red gumballs should then be the 5 pieces because there are more red gumballs. For every 3 white gumballs, I should have 5 red gumballs, which hopefully your brain just screamed at you, hey, that's a ratio thing. So here's another one. This isn't in your math workbook, but take a moment and think about how you could draw a model, a tape diagram, to illustrate the number of cars is 7 thirds the number of trucks. If you need to, look back at example 1, take a look at how they labeled the parts of their tape diagram and then how they drew it. Hopefully we've got in your head, you're seeing number of cars and number of trucks, and so you would label cars and trucks. And the number of cars is 7 thirds the number of trucks. I have more cars than I have more trucks. So I need a bigger tape diagram for cars than I need for trucks. And then I notice that the 3 here is telling me the parts for the truck. So there are 3 of them, which means that the 7 is telling me the parts for the cars. 1, 2, 3, 4, 5, 6. 7 thirds. Now this 7 thirds is our ratio of 7 to 3. The ratio of the cars to the trucks is 7 to 3. But when we write it as a fraction, now all of a sudden we have a number that we could use for multiplication, we could use it for addition, we could use it for subtraction. We've all of a sudden taken this ratio and we have turned it into a value, a number that we can use for computation. All right, example 2. So we're going to look through some ratios here, connect it to some fractions, and start to think about values here. The duration of 2 films are modeled below. So we have film A, we've got film B, and we've got some tasks we need to perform. And the first question is the ratio of the length of film A to the length of film B. So film A has 1, 2, 3, 4, 5 units, and film B has 1, 2, 3, 4, 5, 6, 7 units. There's our ratio of 5 to 7. Worked on this lots and lots. And now we're going to state this as a value. The length of film A, and we have a fraction of the length of film B. Well, let's make a quick comparison here. So here's film A, and it's got 5 units in it. If we were to put those 5 units in film B, we would say that film A is how much of film B? What fraction of film B is film A? So we look at this and we say, okay, we've got a fraction. Okay, film A and film B aren't the same length. Film A is a part of the length of film B. So film A is 5 parts of the 7 that it would take to make film B. So film A is only 5 of the 7 pieces that it would take to make film B. Now we can turn that around and we can go the other direction. The length of film B. So here we've got film B and it's got 7 parts. And film A only has 5 parts. So film B is going to be longer than film A. So I'm going to need a fraction that shows that film B is longer than film A. film A only has 5 parts, but film B has 7 parts. So for every 7 parts, units of film B, there are 5 of film A. It is 7/5 the length of film A. 5/5 would be film A, but we have 2 more. So we have 7/5. So once again, we have built this connection. We've got this ratio, this 5 to 7. Or we could turn it around and say the ratio 7 to 5 if we were talking about the ratio of film B to film A. But instead of writing as a ratio, we are making a connection to fractions. And I hope that you can see the fractions here. It's really, really important that you can see that film A is a fraction of film B. It is 5/7. And that you can see that film B is a fraction of film A. It is all of film A plus 2 more fifths. All right, so we're going to use this now to try and solve some problems. And we're going to kind of step through exercise one step at a time here. So Sammy and Caden went fishing using live shrimp as bait. Sammy brought 8 more shrimp than Caden brought. And when they combined their shrimp, they had 32 shrimp altogether. Now, the first part of this we want to answer is, how many shrimp did each boy bring? Oh, sorry, this isn't the first part. This is a question we want to answer. Now, there's lots of different ways to figure out how they did this. You could use a guess and check. I'm going to show you quickly a way that I approach problems like this. I know that Caden brought less than Sammy. So Sammy's got more, and Caden's got less. So I've got Sammy, and I've got Caden. And I know that if I combine it all together, the total is 32. But I know that Sammy brought more than Caden. And I know that that difference is 8. So looking at my tape diagram, I can say, okay, they have a whole bunch that is the same. Now, if we take away how many more Sammy brought, if we take 32 and we take away the difference, we're left with 24. These 2 pieces here are the 24 shrimp. And these pieces are the same size, which means that each one of these pieces is worth 12. So I have Caden brought 12, and Sammy brought 12, but Sammy then also brought 8 more. And I can do a quick check here. Sammy brought 20, and Caden brought 12. Is the total 32? 20 plus 12 is 32. Does Sammy have 8 more than Caden? So I want you to notice here how a tape diagram helped me see that the 8 was what was different between the two, which left me with 2 sections here that I knew was going to be 24 because I took the different part out, the 8. And the 2 sections, 24 divided by 2 is 12. So we've got Sammy with 20 and Caden with 12. All right. I'm just going to leave some notes up there. All right. So the ratio of the number of shrimp Sammy brought to the number of shrimp Caden brought. Well, I know that Sammy brought 20 and Caden brought 12. All right, so we've got a 20 to 12 ratio. Now express the number of shrimp Sammy brought as a fraction of the number of shrimp Caden brought. So we need to start thinking here about how we're going to take these 2 ratios and we are going to write them as a fraction. Now hopefully your brain has already clicked when we did those first couple of models and you're thinking in your head already, hey, this is 20 twelfths. 12 is the total of what Caden brought. So it's 12 parts. 20 is what Sammy brought. Sammy has 20 twelfths of what Caden does. Now, if you needed to, you could actually draw it all out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Excellent. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here's 20, and here's 12, and I could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These 12 here are equal to these 12 here. So that would be equal to 12 twelfths. But Sammy then has 8 more, so he has 20 twelfths of what Caden does. The ratio of the number of shrimp Sammy brought to the total number of shrimp. Well, we know that Sammy had 20, and we know that Caden had 12. We know that the total number of shrimp is going to be, I shouldn't write those with ratio symbols. Sammy is equal to 12. Caden is equal to, I am having a rough go. Let me try again. Sammy is equal to 20 shrimp. Caden is equal to 12 shrimp. The total number of shrimp is 32. There we go. And the ratio of the number of shrimp Sammy brought to the total number. Sammy is 20 to 32. Now, the next question is probably going to be, what is the fraction? What fraction of the total shrimp? What fraction of the total shrimp did Sammy bring? Well, we know that the total number of shrimp brought was 32, and we know that Sammy brought 20/32 of those, 20 out of 32. So in exercise 1 here, what we've done is we've spent a lot of time just coming up with ratios and writing them as fractions. In the next exercise, we're going to take a next step here, and we're going to start using this information a little more. So a food company that produces peanut butter decides to try out a new version of its peanut butter that is extra crunchy, using twice the number of peanut chunks as normal. The company hosts a sampling. In other words, they bring in customers and they say, try out our peanut butter and tell us which one you like better. And they find that 5 out of every 9 customers prefer the new extra crunchy version. Now, I hope by now that your brain just screamed at you, hey, there's a ratio. And right now, I need you to brainstorm what part-to-whole or part-to-part ratios can you write to represent this situation? Go ahead, make sure you try and do that. What part-to-part or part-to-whole ratios can you write? Well, one part-to-part that we could write is, let's do part-to-whole first. The new extra crunchy and the total number surveyed. The new extra crunchy, we had 5 who preferred that, and the total number of customers was 14. The ratio of the number preferring regular to the total, so we had 4 who preferred out of 14. Now, hopefully right now your brain is screaming you, wait. Where did 14 come from? Excellent. There aren't 14 people surveyed. It says 5 out of every 9. 9 is the total. We are not going to add these two together to find a total. The number preferring the new extra crunchy to the total number is 5 to 9. Now, if 5 picked the new extra crunchy, then the other 4 must have picked the regular crunchy, because there were only 2 types of peanut butter they were sampling. The ratio of the number preferring regular crunchy to the number preferring new extra crunchy. Well, we know that there are 4 parts that prefer the regular, and we know that there are 5 parts that prefer the new extra crunchy. And the new extra crunchy to the regular is 5 to 4. So we have 4 ratios that are part to whole or part to part. Notice we didn't do any whole to part ratios. Right now it was just part to part and part to whole. Now we're going to use the value of the ratios. So we're going to think about turning these into fractions to make these multiplicative comparisons. The number preferring new extra crunchy is 5/4. Remember our ratio is 5 to 4, which means that there were 4 total parts for the regular, and we had 5/4 of those that preferred the new extra crunchy. So we have this 5/4 here. Now, when we talk about this as a multiplicative comparison, that means that we can use this as part of a multiplication problem to answer questions. And we'll look at that in a minute. But I want you to start seeing that these fractions are going to be useful for multiplication. The number preferring regular is 4/5 the total number surveyed. Is it 4/5 or is it 4/9? Oh man, I am such having a Friday here. Of the total number surveyed, 5/9 preferred the new, 4/9 preferred the regular. Now I've got my regular, 4/5, and that new extra crunchy is 5/4. Boy, it is a Friday. We'll see if I can manage to get through this lesson without messing up too much more. So we have our fractions. Now we're going to take a look at how can we use these fractions to help us solve problems. All right. The company is planning to produce 90,000 containers of crunchy peanut butter. So the total number of containers they are going to produce is 90,000. How many of these containers should be the new extra crunchy, and how many should be the regular crunchy? So they don't want to produce too many of either one. They want to get the just right amount. So they're going to use this ratio, this 5/9, to help them figure out how many of each they should produce. Now, it would be really helpful because I really don't want to draw a tape diagram of 90,000 containers of peanut butter and have to count them all up. It would be really helpful if we had some mathematical way of doing this. And by mathematical, I mean if there was some way we could add, subtract, multiply, or divide to answer this question. Which leads us to this: does one of our comparison statements above help us? Well, we said that 5/9 of customers preferred the new. So wouldn't we want to have 5/9 of the containers to be the new extra crunchy? And couldn't we take the actual number of containers, 5/9 of 90,000, and find out that that is how many of the new extra crunchy we should produce? And at this point, you should look and say, hey, that looks a lot like multiplication. The word of is a great multiplying word. So we want 5/9 times 90,000. So these statements we can start to use to answer questions. 5/9 of the 90,000. I'll quickly show you a way to multiply this. 5/9 times 90,000. Let me write it this way. 5 and 90,000 breaks into 9 times 10,000. So here's my 5/9. Here's my 90,000. The 9s are going to divide each other. 9 divided by 9 is 1. That's going to leave me with 5 times 10,000, which is going to leave me with 50,000. So I know that I need 50,000 of the new, and that means the other 40,000 are going to be the regular or original. All right, let's look at it a different way. So the company decides to produce 2,000 containers of regular crunchy peanut butter. How many containers of new extra crunchy peanut butter would it produce? Well, let's think about our ratios here. We know that the regular is 4/5 of the new. Remember, this was our fraction we came up with a couple problems ago. And we know that the new is 5/4 of the regular. So which one of those two would help us find the information asked for in the question? They're telling us that we're going to have 2,000 of the regular. So wouldn't it be useful to know 5/4 of the regular? 5/4 of the regular. I have the regular and I want to find 5/4 so that I can know the new. So 5/4 times 2,000. And I'm going to take the 2,000 here and I'm going to split it into 4 times 500. So I've got my 5/4 here and I've got my 2,000 here. The 4s will divide, which is going to leave me with 5 times 500, and I'm going to find out that I need 2,500 containers of the new extra crunchy peanut butter. Now you could use a tape diagram to do that. So we need 2,000 containers, and it says that our ratio is 5:4. So I can take the 2,000 divided by 4, 1, 2, 3, 4, and I would find out that each unit is worth 500. And I know that this is 5 units, and each unit is worth 500. So you'll also notice that we've got our C value, our little c, our constant, and then I can find that this is 2,500. So there are a couple of different ways to think about this once we find the value. All right. Company decides to produce 10,000 containers of the new extra crunchy peanut butter. How many containers of the regular? I know that the regular is 4/5 of the new. And it says the new is 10,000. 4/5 of 10,000. Now, tape diagram wise, I've got 10,000. And it says that I want 4/5 of the 10,000. So the 10,000 is going to have to be divided into 5 pieces. 1, 2, 3, 4. So I've got 5 pieces. 10,000 divided by 5 tells me 2,000 in each one of these. And I want 4 of those. 2, 4, 6, 8, 8,000. So if I have 10,000 containers of the new extra crunchy, I would have 8,000 of the regular. I could also do 4/5 times 10,000. And I'm going to take the 10,000 and split it into 5 times 2,000. 4 times 5 times 2,000. So the 5s will divide out, and that'll leave me with 8,000. All right, the company decides to produce only 3,000 containers of new extra crunchy peanut butter. How many containers of the regular? I know that the regular is 4/5 of the new. So I want 4/5 of 3,000. 4/5 of 3,000. On a tape diagram, 4/5 of 3,000. The 3,000 needs to be split into 5 pieces. 1, 2, 3, 4. 3,000 divided by 5 gives me 600. And I want 4 of those. 600 times 4 is 2,400. 2,400 containers of the original. All right, I know that this is kind of a mind-blowing lesson. You'll probably want to go back, look at different problems, watch again kind of the thought process, but there's a couple of things that, well, they're in the I can statements, things we really need to pay attention to. We need to understand ratios written as fractions. We need to recognize that the ratio of 2 to 3 is showing us 2/3. This 2 right here is 2/3 of this. And this 3 here is 3/2 of this. So we need to be able to take ratios, write them as fractions, and understand what that means. And then we need to be able to take fractions and write them as ratios. We know that 2/3 is equal to the ratio of 2 to 3. 2/3 of something. Here is 2/3. Well, that's the ratio of 2 to 3. Once we've done that, we're now looking at the value of a ratio. Once we get that fraction, we have a value. And when we have the value, then we can start to stick it into problems and solve problems. And we touched on part to part, part to whole. For example, our ratio of 2 to 3. Our ratio of 2 to 3. We've got 5 total parts. So I have my 2 out of 5 and my 3 to 5. So starting to look at part to whole ratios. All right, learning targets. Once again, we are really focused on this making comparison stuff. Part to part, part to whole, whole to part, really focused on these sections here, and we stepped into using those to solve problems. Lesson summary, so, and this is very wordy here, for ratio A to B, we're often interested in the B to A. So if I know I've got 2 to 3, then I'm probably also interested to know in the 3 to 2. If A and B can be measured in the same unit, I can do some combining stuff. So if this is 2 cups and this is 3 cups, now I have 5 cups. I can do some comparison. This is where I create my part to whole ratios. And then we've got some example here. If Tom caught 3 fish and Kyle caught 5 fish, we've got the ratios that we generate from this, part to parts and part to wholes. And then we have a statement of what is the value. For the ratio A to B, and B cannot be 0, the value of the ratio is the quotient of A divided by B. The value of the ratio is the division problem. So 2 divided by 3, or 2/3. All right, so that concludes Module 1, Lesson 7. Lots to think about there. We'll be continuing to explore that in the next few lessons. If you've got questions, make sure that you talk to your teacher, give your problem set a try.